Good afternoon. I am Mr. Ish. You are looking here at what will be a very useful video, because even if something like this doesn't show up on an exam, like a standardized test, something like this very likely will show up in your perhaps 12th grade algebra class, even advanced mathematics. Some of you may have heard of this Pascal's triangle and some of you may not have. We're talking here about symmetrical binomials, a plus b to the power of n, or in the same terms, x plus y to the power of n. You expand this binomial, and how do you expand it? By means of the Pascal's triangle. That's what this video is about. A very useful tool to expand binomials which are large. We know a very familiar easy expansion here: x plus y whole square is equal to x squared plus 2xy plus y squared. Likewise, you could have done a plus b over here instead of x plus y. All of this is nice and easy. These symmetrical binomials, when the n value here, the exponent is small. The minute that exponent becomes large, then you have to resort to some useful technique. What exactly is a symmetrical binomial? It's one right over here where you have a value in terms of a coefficient of 1. Think about it, you got 1a plus 1b to the power of n. Contrast this to something which looks like 2a plus 3b to the power of n. You no longer have a symmetrical binomial here, but you very well have it here. The Pascal's triangle is very useful for cases where you have a symmetrical triangle. And let's develop this Pascal's triangle, and then we will develop our two questions using that triangle. At the very top of the triangle, we happen to have a number 1, and that develops from a binomial which looks like a plus b to the power of 0. Anything to the power of 0 is always equal to 1. And in the next part, we always have 1 and 1. The outer edges always stay the same. We're talking about the outer edges of the triangle. And as we develop this triangle, I'll tell you the hints that come along, or the trends which develop. This can be developed from a plus b to the power of 1. A to the 1, b to the 1. You got a to the 1, b to the 1. Here you have just 1. Now, the next one, obviously, as you see, the trend is here. We're increasing this n value. We had 0, 1, now we have 2. And you know you're going to have 1 to 1, a squared plus 2ab plus b squared. But how can you develop these internal numbers? This is how you do it. Each of the numbers here within the outer edges is always equal to the sum of the two numbers above it. 2 has two numbers above it, 1 and 1. You add 1 and 1, it gives you this 2. But all of these numbers here along the edges are always 1s. It's only the internal number which is equal to the sum of the two numbers directly above it. What about a plus b whole cube? Well, you know that will be a cube plus 3a squared b plus 3ab squared plus b cubed. You know you have to memorize some of these, so this is one of those which is frequently expected of us to memorize. But you can do it all here with the Pascal's triangle. Just put a 1 here on the outer edges, and then you'll have two numbers show up. 1 plus 2 is a 3, and 2 plus 1 is a 3. Another important trend, you should see this value right here, these n values, the exponents 0, 1, 2, 3. Whatever the exponent is, when you expand it out, it'll always be n plus 1 terms. If the exponent is 3, we'll have 4 terms. If the exponent is 2, we'll have 3 terms. If the exponent is 1, we'll have 2 terms. If it's 0, we have 1 term. You can imagine if you had an exponent of 10, you expand it out, you'll have 11 terms. It's always n plus 1 terms. The outer numbers are always 1. The inner numbers are always equal to the sum of the two numbers directly above it. So our question number 1 is this: using the Pascal's triangle, the trends of the Pascal triangle, develop a plus b to the power of 4. That's our question number 1. Question number 2 will be develop a plus b to the power of 5. Remember, again, this could have been x and y, it doesn't matter. So let's look at a plus b to the power of 4. That's our first question. We'll always start with the 1s on the outside because that trend exists once. Now we're looking at the two numbers directly above it. We have 4 over here, right? Therefore, we must be looking at 5 terms. It's always n plus 1, 5 terms. 1 plus 3 is a 4. 3 plus 3 is a 6. 3 plus 1 is a 4, and here it's done. So how would you say it? Remember, these represent the coefficients of your expansion. You look at these coefficients and you will increase one exponent for a variable as you decrease the other one. This one right here will become a to the 4th plus. You look at the next exponent, you bring that here, you get 4a cubed b to the 1. You're slowly decreasing a exponent by 1 as you're increasing the b exponent by 1. Plus 6a to the 2, b to the 2, plus 4a b cubed plus 1, we don't have to write 1, b to the 4th. Think about it. Here we had b to the 0 and it has increased to b to the 4th. Here we had a to the 4th and it has decreased down here, a to the 0. Everything decreases or increases incrementally by 1. The Pascal's triangle only gives you these coefficients which are present in front of your variables. That's the beauty of this technique. Let's look at question number 2. Question number 2 is what? A plus b to the power of 5. When you're looking at a plus b to the power of 5, we're looking at this n plus 1. We should have 6 terms. And then the Pascal's triangle is giving us our coefficients. You'll always have these ones on the outside. 1 plus 4 is a 5. 4 plus 6 is a 10. 6 plus 4 is a 10. 4 plus 1 is a 5. I've gotten my 6 terms. Now I'll use these coefficients to do my expansion using these. I'll start with a to the 5 plus, now I have a 5, a to the 4. I'm going to start decreasing the exponent on a by 1, but I'll increase the exponent on b by 1. Plus 10 a cube b square plus 10 a square b cube plus 5 a b to the 4 plus b to the 5, and here is our expansion for this. And you can see how the Pascal's triangle has helped you do all of that. Remember again, the outer numbers are always 1. The inner numbers are always equal to the sum of the two numbers above it. Like 6 was equal to the two numbers above it. This 10 was equal to the two numbers above it. These items in the Pascal's triangle are only the coefficients which you see in front of your variables. The actual variable exponents follows a similar trend, such as the a will decrease by 1 as it goes through, and b will increase by 1 in terms of exponent as you take it through, and everything will work out that way. And that will be the end of this video. Keep this Pascal's triangle in your mind. Thank you for watching. Have a nice day.